Assalamu alaikum everyone. So today we will be having lecture number 2 and we will be discussing about transmission fundamentals. So as the title of the course is wireless and mobile computing, so first of all we will be studying the enabling technologies or knowledge that enhance wireless and mobile computing, right? So in this context, today we will be discussing about transmission fundamentals and we will learn about different concepts, right? So as we know that in case of wireless transmission, we use signals for transmitting information, for conveying information from one point to another point, right, or from one point to many point, right? So some of the concepts which are very important, they are related to the signal analysis, right? So we will be studying the signal analysis from the time domain concept, right? And we will also look for frequency analysis of those signals, right? And then we will talk about the relationship between data rate and bandwidth, right? So let's start from the signals, right? So as everybody know that signals are used for transmitting, for conveying information, right? So the electromagnetic signals are used as a source for or as a mean for transmitting information, right? So the electromagnetic signal, it can be a function of time as well as a function of frequency, right? So if we talk about the comparison, right, so the time domain concepts, they are important in order to find certain parameters of the signal, right? And the frequency domain analysis or frequency domain concepts, they are important from some other parameters of the signal, for example, bandwidth, right, and the spectrum, and so on and so forth. But as in this course, we will be focusing on frequency domain concepts of the signals, right, as compared to the time domain concepts, right? So let's start from time domain concepts, right? A time domain electromagnetic signal can be either analog or digital, right? So there are two forms of signals. One is analog signal and the other one is the digital signal. So as we can look around that we are living in the analog world, right? Most of the phenomena, most of the natural processes, they are analog in nature. For example, if we talk about temperature, it's varying all the time, right? Even within this room, we have different temperature at different points, right? And if we talk about the pressure, right, so this is also a varying quantity or analog quantity, right? So it means analog signal is a sort of varying signal, right? So it's varying all the time, right? So if we define the analog signal, then we can say it is the signal whose intensity varies in a smooth fashion over a time, right? Over a time period of time. Or you can say that there are no breaks or no discontinuities are found when we talk about the analog signal, right? So you can see the example right? So on the x-axis we have the time, and on the y-axis we have the amplitude that is represented in volts, right? So you can see that over a certain period of time we have represented the signal, right? And it is varying continuously, right? And there are no discontinuities, right? For example, if we talk about another form of signal, so you can see that here we have right. This is, for example, if this is time and this is the amplitude on the y-axis, right? So if we talk about signal like this, right, so you can see that for each point in time, right, so for example this is t1 and this is t2, right? So these, we have taken these 2 points, and you can see that at those 2 different points in time the signal is varying, right? The amplitude over here is somewhat different from the amplitude at t2, right? So this is the, so let's have a look at the discontinuity, right? So if I have a signal like this and then there is a break and then I have a signal like this, right? So again here we have time. Let me write down the A for amplitude on the y-axis, right? So you can see that we have a discontinuity, right? So we cannot say this, although the parts, in parts this signal is analog, but on the whole we cannot say, or we cannot define this as a sort of analog signal, right? So we can have another sort of discontinuity, right? So if we have, this is the time, and again we have A for amplitude on y-axis, right? So let me, right? So here you can see that there is an abrupt change, right? Right, and there is a reference crossing, right? So from positive to negative, and here we have another abrupt change that is from negative to positive within no time. So those points, these points, they are mentioning the discontinuities, right? So the best example regarding the analog signal is my voice, right, or speech, which is varying all the time. Then we have another type of signal, that is digital signal, right? So is the one where the signal intensity maintains a predefined level for a certain amount of time, right? And then it changes to another level, right? So we have another figure over here, right? So these are the digital waveforms. Again, we have time on the x-axis and amplitude on the y-axis, right? So you can see that this signal is maintaining, right, for this much amount of time. There is no change, right? So here again you can see there is no change, for this period of time, right? So it maintains a constant level for a certain amount of time. So we have a very good example of a digital logic design where we represent ones and zeros, right? So let me draw another figure over here, right? So again here we have time axis and here we have the amplitude, right? So right, so if this is +5 and this is -5, right? So let's say we represent +5 by 1 and -5 by 0, right? So we have 1 over here, 0 over here, and 1, 1. And you can say we are actually representing 1, 0, 1, 1, right? So this is the representation of binary data by using digital signal, and we are very familiar with this regarding digital logic design, right? So then there are certain types of different signals, right? So let's talk about different types of signals, right? So periodic signal, right? So the signal which repeats itself after a certain amount of time, right? So on the left hand side of your slide you can see again we have the time axis on, and then we have the amplitude axis, that is y-axis, right? So you can see that the signal is repeating itself, right? So here this is a typical sinusoid or sine wave, right? So you can see that it is repeating itself, so it finishes over here, right? And then it again repeats itself, and again the second right? So this is the first, right? And this is the repetition of the same signal, right? So if we go on, it will continue forever, right? So on the right hand side of your screen in figure B we have, so this is a varying analog periodic signal, and here we have a digital periodic signal, right? So here we have its completion, right? So it is completed, one cycle is completed over here, and then the same signal is repeating itself, right? So that's why we have mentioned the period, right? So because the amount of time it takes to complete one cycle is called the period, right? So this is periodic signal, right? But in digital domain. So there is a way to represent those sort of signals mathematically, right? So if we represent in time domain a periodic signal by s of t, where t is mentioning the argument, right, or the time domain. So here you can see that we can say this signal s of t is periodic if it's t plus the period, where t is the period, right? So here you can see that this is the period, because in this much amount of time signal repeats itself, right? So again here we have the period for the analog periodic signal, right? So then s of t plus capital T is equal to s of t, right? So you can see that the time period is absorbed, right? So it means we got the same signal, right? So here this is the time period, and we are repeating the same signal again, and it will continue forever, right? So here you can see we have mentioned that the constant t is the period of the signal, and this holds for both periodic and for both analog and digital signals, right? And then we have another type of signal that is aperiodic, right? So in this figure we have a periodic signal, right? So you can see that the signal is finished over here, right? And then again it is repeating itself, so it's a sort of periodic signal. But here we are only having the one part of the signal, right? A part of the signal. So it's a non-periodic signal, right? So we can see that if we have a sinusoid like this, that is the time axis and that is the amplitude, right? So this is not a periodic signal. So again, if you talk about right, so this signal is again, if this is time axis and this is the amplitude, and this is +5 and this is -5, right, in volts, right? So +5 is 1, -5 is 0, right? So 0 +5 is 1, right, and this is 0. So if I have 1 0 1 0, right? So this is a sort of previous case when we have the periodic, but we have only 1 0 over here. So this is right. So this is not repeating itself, right? So both analog and digital can be periodic or aperiodic, right? But whenever we talk about the data communication, right, periodic analog signals and aperiodic signals are used. Both of the signals are used, right? So here we have more time domain concepts, right? Analog signal and so here we have the summary, right? Analog signal, the signal intensity varies smoothly with no breaks, or there are no discontinuities within the signal. And then we have the digital signal. Signal level maintains for a certain amount of time, right, and then abruptly changes to another level, right? So as right, so here let me draw. So this is an example of analog signal, right? And this is the example of digital signal, right? So again we have time axis, and here we have amplitude axis, right? So amplitude, time, right? So there is an abrupt change from plus to negative at this point, and there is an abrupt change. You can see that this signal is maintaining its level either minus or plus, right? This is +5 volt and this is -5 volt for a certain amount of time, right? So then we have periodic signal. So this is a digital signal, right? Then we have periodic signal, right? So this is the example of a periodic signal. Let me show the dots that it is continuing like in this fashion forever, right? So this is analog periodic signal, right? And here, let me show you. Right? So this, so you might got the point, but I want to show you, right? So time axis and the amplitude axis, right? So it is repeating itself, right? 1 0 1 0, so we will be getting 1 0 1 0 1 0, and it continue forever. And then we have aperiodic signal, right? So you can see that the signal, right, that so it can be like any, right? So it cannot, it is not repeating itself, right? So we have both analog and digital aperiodic signals, right? So these sinusoid and cosinusoid, they are very important, right? Whenever we talk about the data communication, so it's a periodic continuous signal, right? So there are different parameters that has to be defined whenever we want to define a sine wave, right? So first we need to know the amplitude, the strength of the signal, right? And normally we represent this in volts, then the frequency, right? So it means how many cycles are being made in 1 second, right? So that is the frequency. And then we also should know the phase, right? So these are the 3 very important parameters when we talk about the sinusoid or sine wave, right? So let me show you those different. So this is a generic sine wave, right? So this is the, you can say, peak amplitude, right? And this is in positive, and here we have again peak amplitude, but in negative, right? So if this is A1, right, then this is minus A1, right? Same amount, right? And then we have to show the frequency, right? So I will be right. So let me define that this is the time in 1 second. So here we have 2 complete cycles in 1 second, right? So this is 1 second, right? So 2 vibrations are being made in 1 second, right? So that is the frequency. Is equal to 1 over t, right? Or we can also have, this implies 1 over f, right? And then we have phase, right? So here the phase is 0, phi 0, and here we have again phi phase 0, right? So let me right? Compare the phase, right? So here we have phi is equal to 0, and here, right, so here the phi is not 0, is equal to some degree, you can say theta degree, right? So it's not 0 over here, right? So here we have different figures, right, mentioning those different parameters which we talked about, right? So here a typical sine wave represented by s of t. This is the amplitude and this is the 2 pi, right? And f is the frequency and this is the phase, right? So here you can see we have time axis, and this is the strength or amplitude, right, in volts, right, and this is time is in seconds. So here we have amplitude 1 and frequency is 1, right? So here one vibration is being made in 1 second, so it means frequency is 1, right? If I go back, so here we have 2 vibrations are being made in 1 second, so frequency is equal to 2, right? So let me write down here f is equal to 2, so this implies t is equal to 1 by 2, right? So 0.5, right? Right, so phi is 0, right? So, and here again on the right hand side, in the upper part of the figure, right, right hand side, we have again s of t, amplitude, right? This is y-axis is mentioning the amplitude, representing the amplitude, and we have time over the x-axis, right? So here we have, you can see 0, 5, 1, 1.5 second, right? So amplitude has reduced. Here we have unit amplitude and here we have 1 by 2, half, 0.5. Frequency is the same because one vibration is being made in 1 second, right? And phi is again 0. So here phi is 0, phi is 0, right? So let's talk about this figure, right? This one. So amplitude is again 1, right? Like this. And but the frequency has doubled, right? So you can see that this is the one vibration and this is the second vibration. So 2 vibrations are being made in 1 second, right? Phi is again 0. So here we have somewhat different phi, right? So you can see we have unit amplitude, right? And unit frequency, 1 hertz, and but phi is different, right? So this is pi by 4, right? So right, so now we have an idea of amplitude, frequency and phase, right? So the frequency is typically represented in hertz, right? And phi, the angle, it is represented in degrees or radians, right? So here another important parameter, wavelength, right? So here we have a wave, normal wave, right? So you can see that we have defined the peak, a crest, and then we have the bottom trough, right? So we have this is a sort of a periodic wave, right? So crest, trough, right? So and we will continue like this way, right? So you can see that how we can measure the wavelength, right? So the distance between two crests, right? So if we define 2 points over here, so 1 point here and 1 point here, right? This one and this one. Similarly, if we have continuity, right? This should be like this, right? So we will be having a trough, right? So we define an so we can measure in another way, right? So this is also the wavelength of the signal, right? Or what in the simplest way, what I can do, right? So for example, I have a wave, right? And I want to know the wavelength, right? So if I take it as a thread, right? And I have a scale here, and then I will measure this, the length of this thread, right? Right? So then this will represent the wavelength of the, right? So this is the scale, typical scale. So we can measure the wavelength, right? So in words, wavelength of a signal is the distance occupied by a single cycle, right? So if I take this as a thread and I can measure this, the length of this thread with a scale, right? Then that will represent the wavelength, right? So we can also say that this is the distance between 2 points of corresponding phase, right? So here we have the corresponding phases, right? And here again we have the corresponding phases, right? So this is the corresponding phase, right? These are the corresponding phase, consecutive cycles, right? So if the velocity of the signal is represented by V, right? So we know the typical formula, S is equal to Vt, right? Where S is the distance, V is the velocity, and T is the time, right? So then if I replace, right? So wavelength, that is the distance between two waves, lambda, and here we have the signal velocity, right? So F is equal to Vt, right? But when we talk about the electromagnetic radiations, and they travel with almost the speed of light, right? So lambda is equal to Ct, right? And we also know that there is a relationship between time and frequency, right? So it means lambda is equal to C over F, right? Or C is equal to F, lambda F, right? Right, so this is the relationship between the wavelength and frequency and velocity. So here comes frequency domain concepts, right? So all the signals, they are actually made up of different frequencies, right? So if I draw right, so this signal is made up of different frequency components, right? Similarly, if we talk about this, so you can see there are different abrupt changes, so this signal is also made up of different frequencies, right? But there should be a mathematical representation. So normally we represent a signal, right, like this, right? So you can see that here we have f, that is normally called the fundamental frequency, and here we have 3f, right? So another component, and it is an integer multiple of the fundamental frequency, right? So these are different components of this signal, right? So first component having frequency f, and the second component having frequency 3f, right? And as I mentioned, the second component is an integer multiple of the first frequency. So the first frequency is called the fundamental frequency, right? So here we have right, so you can see that this is the sinusoid with frequency f, right? So you can see that here we have one. So the frequency is different over here, right? So here we have, so this is one wave, and this is the 2, and this is the 3, right? So now the frequency has been tripled, right? So if this is f, and here we have 3f, it's 3 times more, right? So signal is repeating 3 times faster than this, right? So if I add those components, right, so this is frequency f, and this is the frequency 3f, right? So you can see the superimposition of those two signals, right? So you can say that this is a sort of right square wave, right? So how we come to know that how many components having what frequencies are there, for example, in this signal, right? So in order to do that, we need some tool, and that tool is Fourier analysis, right? So we need to analyze the signal in frequency domain, right, by using Fourier as a tool in order to know the frequency components contained by a particular signal, right? Okay. So again, the same example, right, showing that here we have a much more clear picture, right? So this is frequency f, and this is 3 times, frequency is 3 times than f, right? And this is the addition of those two components in order to get this, right? So you can see that we have C is the sum of f and 3f, right? Right. So again here I have shown, so this is like, for example, the fundamental frequency, right, f naught, and then we have the other frequencies that are integer multiple of the fundamental frequencies, right? So here 2f naught, right? And you can see that this signal is much more faster than this one, right? So you can see that more vibrations are being made in the same amount of time, right? So again here this is 3f naught, right? So f naught fundamental frequency, and this is the integer. So this signal, this component is the integer multiple of the fundamental frequency, right? So 3f naught, right? So this is the frequency domain, and here we have the sum, right? So if I add up all three components, right, or you can say I superimpose, I must say rather superimpose those signals, I will get this sort of signal, right? Or in other words, you can say if I have this signal in time domain, right, and I want to know what are different frequency components that are being present within this signal, right? So in order to do that, I need to switch from time domain to the frequency domain, right? So how I can do that? I will be using Fourier as a tool, and I will be analyzing the signal by using Fourier, right? So here again we have the same idea, right? So here we have time domain and amplitude, right? And this is representing the frequency, right? And this is the signal. So this is the time domain representation, right? So we have this signal, main signal, right? And these are the components, right? F naught, and this is the maybe integer multiple of the fundamental frequency. This is the fundamental frequency, and this is the integer multiple of the fundamental frequency, right? And this is the frequency domain, right? And you can say these are the components, different components, right? And here is the frequency domain representation, and we can see that we have only two peaks, right? So if this is the, so if we want to plot the signal in frequency domain, so we will get those peaks, right? So we will superimpose those two frequency components, and we will get this as a result, right? Okay. Right. So as I have mentioned, the frequency domain can be obtained through the transformation from one, it can be a time domain or spatial domain, to the other via Fourier transform, right? And we will be using Fourier transform as a tool. The example, MPEG audio, right? So we need Fourier analysis when we use Fourier as a tool when we are having the audio in the form of MPEG, right? And DCT, discrete cosine transforms, right? That is being used when we talk about the JPEG, that is a technique for representing images, right, still images, and MPEG, that is the moving video, right? So we use discrete cosine transforms, that is a special case of Fourier transform, right? Okay. So let's talk about an example, one-dimensional example, right? See what different domains means. Consider a sound, noise of a car horn, right? So this is sort of sound. So we can describe or represent this sound in two related ways. We can sample the amplitude of the sound many times a second, right? And as a result, this will approximate the sound as a function of time, right? And there is another way. We will be analyzing the sound in terms of pitch of the notes, right, or frequencies. So this is a sort of, this is the time analysis and this is the frequency analysis, and that make the sound up recording the amplitude of each frequency. Like here you can see, we can see that at this frequency the amplitude high is higher, but at this frequency the amplitude is a bit lower, right? So over here again we will be recording the amplitude of different frequencies or each frequency, right? Then we have another example of a sine wave that has a frequency of 8 Hertz, right? Right? So 8 Hertz means that wave is finishing 8 cycles in a unit second, right? So that means the frequency of that wave is 8 Hertz. So from, if we talk about the frequency domain, right, we can see that the composition of our signal is one wave, one peak occurring with a frequency of 8 Hertz with a magnitude fraction of 1, that is, it is the whole signal, right? So here is the graphical representation, right? So we have the time domain and you can see the frequency domain. So at this frequency you can see the peak amplitude, right? Right. So here the superimposition of sine waves has been shown, right? So you can see that this is the fundamental frequency and these are the integer multiple of the fundamental frequency, right? For example, this is f0, right? And if this is one wave and the same amount of time, this is 1, right? And this is 2 and this is 3. You can say 3f0, right? So 1, 2, 3. So here we have 1, 1, 2, 3, 4 and 5, right? So 5 f0, right? So you can see that we have to superimpose, right? So this is the fundamental frequency f0 and this one is 3 f0 and here we have the 5 f0, right? So the resultant can be a wave like this, right? It should be a square wave, right? Right, so here we have another example, right? So again square wave, right? So you can see that a digital signal 200 Hertz is the frequency, may be composed of that is 200, 600, 1000, 1400, 1800, 2200, 2600, 3000, 3400 and 3800 sinusoidal signals, right? So let me do something different, that is I will take 200 as common, right? So I will left with 1, 3, 5, 7, 9, 11, 13 and then 15, 17 and 19, right? So if I multiply this with f, that is f, 3f, 5f, 7f, 9f, 7f, 13f, right? And 17f, 19f, right? So, and this f is actually this common factor, right? So that is the fundamental frequency. Let me write down fundamental frequency, right? So actually this is a square wave, right? If I, right, so this is a sort of square wave. So if I, and this is, for example, the, for example, you can say this is the time domain representation of a square wave, right? So if from the time domain I move to the frequency domain, right, so I will be getting those different frequency components, right? Okay, so let's talk about spectrum, right? Spectrum is very important terminology, right? So the spectrum of a signal is actually the range of frequencies that it contains, right? And how we get those different ranges of frequencies, obviously, for example, if I have a signal in time domain, right, and I want to know the spectrum of that signal, so I will take the Fourier, right, and we'll go to the, for example, frequency domain, and this is f1 and this is f2, right? So that the difference of those frequencies is actually the spectrum, right? So here we have the frequency axis, right? F, this is F, right? This one. So how the frequency spectrum is generated via Fourier transform of the signals. The same we have done over here, right? And so you can see that we have the range of frequency, and that is representing also the amplitude, right? So at this central frequency we will having the peak amplitude, right? Okay, and there is another important parameter, that is phase, that is also plotted versus frequency, right? So we can also have the idea of the phase, right? So as an example, a source of light can have many colors mixed and different amounts, right? So the intensity, right? Rainbow or prism send the different frequencies of white light in different directions, making them visible individually at different angles, right? So if we plot the intensity against the frequency, right, so we will get the amount of each color, right? So that amount is the frequency spectrum of the light, right? Okay, so here we have a visible or you can say we have the electromagnetic spectrum, right? So you can see that we have energy and the wavelength, right? So it means, as we know, we have a relationship between C mu lambda, right, or lambda f, right? So let's see right? So this is how we drive the, right? So you can also represent f frequency as mu, or you can also use f, right? So you can see that as the wavelength is increasing, right? So here we have the wavelength increasing, the frequency is decreasing, because if we talk about c, that is the velocity of light, right? And that has to be a constant, right? So if lambda frequency, or we talk about the wavelength, right? Because it is mentioned wavelength over here. So wavelength is increasing, right? So one factor is increasing, right? So remember that this is a constant, so that has to be decreased, right? So, and this we will talk about at a later stage. Energy, what is the relationship between energy and those different parameters, right? So or on the other hand, if we move here, right, so it means frequency is increasing, right? So this has to decrease, but c has to be a constant, right? So here we have the visible light spectrum over here, right? So you can see that we have radio wave, microwave, infrared, and this is the visible spectrum, right? So that can be seen by the human eye. That is the light, right? Visible spectrum, right? So we can have an idea. Wavelength, so wavelength is increasing in this direction and decreasing in this direction, right? You can see that the waves are becoming more and more dense over here because the frequency is rising over here in this direction on the right hand side of your slide, right? So here we have radio, microwave, infrared, visible. This is the visible light spectrum, ultraviolet, X-rays, and gamma rays, right? And this is the frequency, right? So you can see the frequency is rising in this direction, and here we have the visible light spectrum. So here we have the visible light, right? So red, orange, right? And you can see that it has frequency is lower here, and it's increasing, right, from red to violet, right? And you can see that the frequency is rising, right? So but the wavelength is here, frequency is rising in this way, right? And wavelength is increasing, and here wavelength is decreasing, right? So the sunlight is being passed by the glass prism, and it is showing red, orange, split the light in 7 colors, right? Red, orange, yellow, green, blue, right? Indigo, violet, right? So, and here we have the wavelength range and frequency ranges for different colors, right? So here we have the whole story, electromagnetic spectrum, right? And these are the references, right? So you can see that the wavelength, it's increasing, right? So the wavelength can be the size of a football ground, it can be size of a man's height, right? 1 to 10, and then we are decreasing, right? 1 feet, baseball, centimeters, right? And then we have pencil thickness over here. So these are the references. And then here we have the atom, right? Because the distances are very shorter, right? Very, very low between atoms, right? molecules and viruses, right? So, and these are the wavelengths, and here we have the frequencies, and you can see that we have the radio spectrum, its utilization, FM radio, mobile phones, right, radars, and different technologies and their utilization, right, ultrasound, right, for medical imaging, and then we have the sound waves between 20 Hertz to 10 kilohertz, microwave oven, right, wireless communication. So this is all being done in the radio spectrum, right? So here we have the infrared, ultraviolet, X-rays and gamma rays, right? You can see the X-rays for imaging, right, medical imaging, medical X-rays, right, and crystallography, and here we have gamma rays, cosmic rays, right? Okay, so this is the whole story of the electromagnetic spectrum, right? So the spectrum is a very precious resource, right? So its allocation is a very difficult job, right? So you can see the complications that are being involved in the frequency allocation, that is actually the spectrum allocation, right? So it's a very precious resource if you use the spectrum effectively and efficiently, right? So the countries which are doing that, they are making a big money, right? And then spectrum bandwidth, right, is so here we have the different bandwidths involved in different spectras, right? So you can see that we have a very overcrowding over here, right? So there is very thin lines between those different spectrums, right? So the absolute bandwidth of a signal is the width of the spectrum, right? Or you can say it's simply the bandwidth, right? So what the absolute bandwidth is, right? So the difference between two frequencies, right? So let me again. So we have a signal like this, right? So this is mentioning F1 and this we have F2, right? So the bandwidth of this signal will be F2 minus F1, right? So the amplitude is 0 otherwise, or it has no meaning for us, right? So here we have a band limited signal, right? So that is using this bandwidth only, right? So again here, if we talk about the spectrum bandwidth, right? So you can see here we have the frequency F, right? And here we have the frequency 3F, right? So obviously, if I plot, right? So let's I have a shape like this, and that is, this is just to show you people 3F, right? So obviously 3F is on the higher side, right? So the effect bandwidth here is 3F minus F is equal to 2F. So the actual bandwidth this square wave requires in order for its transmission is 2F, right? So this is very, then the effective bandwidth, right? So as we have mentioned that many signals have infinite bandwidth. How, right? So if I have a signal over here, and right, so if I, this is the time and this is the amplitude, right? So I will take I will move into the Fourier domain, right? So this is, for example, f naught, right? One, 2 and 3 f naught, right? 1, 2, 3, 4 and 5, right? So that is 5 f naught, right? And so forth. So we can have infinite frequency components that are being present if we dissolve, or if we want to find out the frequency components, right? So but the difference is that most of the energy of this signal will be contained in first few frequency components, right? So that's why we normally ignore the rest of the frequency components, right? So so as a whole, each signal can be represented by infinite frequency components, but most of the energy is contained in the first few components. That's why we say the signal can have the infinite bandwidth, right? But most of the energy is contained in a relatively narrow band of frequencies, right? And that narrow band is actually referred as the effective bandwidth, or just the bandwidth, right? So then we have the DC component, right? So every periodic waveform has three main components: the DC component, a sinusoid, right, and the integer multiple of those sinusoids, right? So again, if we have a signal over here, right, and we decompose that signal, so this is time domain, and this is the, here we have the amplitude. If I move into the frequency domain, right, so we will be having a DC component, right, and then we have here, right, that is the DC component, right, that at 0 frequency, and then we will be having some other amplitudes, for example, like this, right, maybe like this. So this is at f1, f2 and f3, right? So each periodic waveform, right, it should have three components: a DC component, that is the amplitude at 0 frequency, and the sinusoid, right, or the fundamental frequency, that is the amplitude that is being represented at f1, the fundamental frequency, and then we have the integer multiples. So here we have f2 is equal to, might be 3f1, and f3 is equal to 5f1, right? So here we have shown a signal with DC component, because before we don't have shown any signal having a DC component, right, or showing an amplitude at 0 frequency, right? So here you can see that we have a DC component, right, and then this is the fundamental frequency, and here we have the integer multiples of, so if f, 3f, and so forth, right? And this is the conclusion, right? So spectrum, range of frequencies contained in a signal, then we defined the absolute bandwidth, width of the spectrum, right, or the effective bandwidth, or we can simply say the bandwidth, right? So this is a narrow band of frequencies containing most of the energies, and we ignore the components that have no effect or impact in order to reconstruct the signal in time domain, right? And then we have defined, or we have mentioned, that each periodic signal have three components: DC component, right, that is the amplitude at 0 frequency, and then the fundamental frequency, right, and then we have the integer multiples of that fundamental frequency, right. So that's all for today's lecture. Today we have discussed the transmission fundamentals. Actually, electromagnetic signals are used as a mean of conveying information in wireless communication or in wired communication, right. So hence they act as an enabling technology for wireless and mobile computing, right. So we discussed about the time domain representation of those signals, and then we also talked about frequency domain representation and how we switch from time domain to frequency domain, and what are the different parameters that are being involved, right, or that we are actually interested in when we switch from time domain to frequency domain, right. And then we talked about the spectrum of signal, right, and we discussed spectrum bandwidth or spectrum width, right. So that's all. अपना ख्याल रखिएगा. अल्लाह हाफिज़. अस्सलाम वालेकुम.